Hello, this is the first unit on regularization and generalization. And everything in this unit is going to be stuff that was well understood, 30 years ago or much earlier. So in some sense, this is review of material that is in a basic machine learning class. The first thing we're going to do is talk about training data, validation data, and test data. These are very standard concepts from machine learning. Good performance on training data does not necessarily guarantee good performance on test data. And when I was in high school, I was exposed to the idea or the fact that an nth order polynomial can fit n training points exactly. And it was very clear to me at that time, just intuitively obvious, that the fact that you've fit n training points with n parameters doesn't say anything about your ability to predict future training points. So this is the overfitting phenomenon, and it's obvious, I think, in that context. If you can fit noise, you're not going to be able to predict. Now, I'm going to make some points here that have to do with difference between the log loss and error rates. We have our fundamental equation, and our fundamental equation is being trained by this cross entropy loss. And people will often use the term loss. When they just say loss, they typically mean cross entropy loss. And then they'll talk about error rate. So error rate is, you predict the most likely label, say if you're doing ImageNet classification, and how many times do you get it wrong? Or if you take the top 5, how many times is the correct label in that top 5? And we're going to talk at some point about algorithms that try to directly optimize an error rate or a blue score or something other than the log loss. But training on the fundamental equation on the cross entropy is by far the most standard thing to do. Okay. In deep learning, the first form of regularization, and probably the form of regularization most commonly used still, is called early stopping. During SGD, one tracks validation loss and validation error. So you've got your training data and you've got your validation data. And you're going to stop your training process when your validation error starts to increase. It's going to come down for a while as you're training, you're getting better, but eventually it's going to start to overfit on the training data, and the error on the validation data will start to get worse. And one thing that happens is that if you're tracking both the cross entropy on your validation data and you're tracking the error rate on your validation, the cross entropy will start to go up before the error rate starts to go up. And you want to stop, if you're in a bake-off, if you're trying to win some competition and that competition is evaluated by error rate, you want to stop when the error rate starts going up. Now, for a long time, going way back, at least 30 years, people have realized that if you tune an algorithm by figuring out which algorithm performs best when trained on the training data and evaluated on the validation data, you can overfit the validation data. You can pick an algorithm that happens to work on the validation data, but then if you pick fresh data, it won't work as well as it works on the validation data. So Kaggle, some of you may be familiar with Kaggle, it's this company that holds competitions, and it sells these competitions to people who want to build algorithms, and then it challenges people from the machine learning community to compete, and then the winning competitor gets passed to the person, the company or whatever, who sponsored the challenge. Anyway, Kaggle withholds a final test data from everyone. It provides training data and validation data, and you can do your algorithm development and hyperparameter tuning with that validation set, but they don't give you the test data. So then, and it's inevitably the case that everybody's validation error or loss is much worse than when you get fresh data, because people will tend to overfit the validation data. Why is it, I said earlier that the log loss will start to go up before the generalization error typically starts to go up. And what's happening there is that as you get more and more accurate on your training data, the model is trained to try to I mean, there's this theorem that says that the cross entropy loss, when measured on the population, on real test data, the optimum on the population on test data is the test data's probability distribution. That means the optimum on the training data is the training data's probability distribution. And as it gets better and better at that, it becomes more and more confident, right? It assigns higher and higher probabilities to the true labels. And this overconfidence effect hurts it on validation or test data. And it hurts it even if its error rate is not getting worse. So that's an intuition that it's generally true that when you train a model on cross entropy loss, it becomes overconfident. And it will be overconfident even on the test data, even when it's wrong. So anyway, this is explaining why you want to early stop based on the error rate rather than the log loss. Okay, so early stopping is great. You should always do early stopping. There's no reason not to do early stopping. But you might be able to change the learning algorithm so that it's sort of more robust against overfitting. Take overfitting, build a guard against overfitting into the learning algorithm. And the first thing we're going to study as a way of doing that is L2 regularization, also known as shrinkage. And we're going to see why it's called shrinkage. So here's the general setting. I'm going to assume that our training data is XY pairs. And we're trying to build a model that predicts Y from X. So X could be an image, Y could be one of 1,000 labels. I want to predict the label given the image. And this analysis is going to be Bayesian. And the reason for that is that the Bayesian analyses are simpler. And I'm going to do a Bayesian analysis that's going to have it's going to give the right qualitative answers, even though I'm going to eventually move to very non-Bayesian, very frequentist analyses, pack-Bayes analyses. But the Bayesian analysis has good qualitative properties. So we're going to do that first. So from a Bayesian perspective, I've got some training data. I've got XY pairs that I'm training on. And I want to maximize the probability of the parameter value given my data. So this is my model. I want to find the model that's most likely given the data. And there's this general thing that if you want to maximize, find the maximum probability for if you want to find the model of maximum probability given the data, it's sufficient to consider the maximum joint probability of the model and the data. This conditional probability is the joint probability divided by the probability of the data. And the probability of the data does not depend on the choice of model. So you can take that out of the optimization. And this argmax is the same as maximizing the joint probability. Okay, now the joint probability can be turned around. You can say, what's the probability of the model and what's the probability of the data given the model? And so it's equivalent to maximizing this, right? And we're trying to find the particular model that so this is maximum a posteriori probability, or MAP. We're trying to find the particular model that maximizes this joint probability. So this is the same as, we're assuming that the data is drawn independently, IID. Each XY pair is drawn independently of each other XY pair. So this probability can be written as the probability of the model times the product over all these pairs of the population probability of the X, and the probability, the model probability for the conditional probability of Y given X. So I'm assuming that the model is only governing this conditional probability. And the probability distribution we're talking about is under that model. That model defines the probability distribution on the data which is you draw the x's from the population and predict the y according to the model, generate the y according to the model. That's our overarching probability distribution that this analysis is being done relative to. Now, the probability of x does not depend on the model. So we can drop that from the optimization problem. So the optimization problem just becomes argmax over the model, the probability of the model times the product over all the data points, all the xy pairs, the probability of y given x. So this becomes our optimization problem. So here's our optimization problem, just rewriting it again. I can take the argmax of this is the same as the argmax of the log of that, or as the argmin of the negative log. So if I take the argmin of the negative log, these products turn into sums. This first term becomes just exactly our cross entropy loss, right? This is exactly our cross entropy loss. But we've also got this prior term, minus log the prior probability of the model. So we're being Bayesian, so we're assuming some prior probability on the model. That's something we have not done before. We just treated the model, all models are equally good as long as they fit the data well. Now we're saying, no, some models are better, more likely than others. And we're gonna take a Gaussian prior. So we're gonna take the prior probability to be proportional to the exponentiation of the norm of the parameter vector squared divided by some variance, 2 sigma squared. Okay, so this is a Gaussian prior, a Gaussian distribution on this. Now, this is going to have some constant of proportionality that's going to disappear. So what I'm doing now is I'm taking this log, minus log probability, and I'm taking minus log of this probability, and minus log of that is turning into the norm of the parameter vector squared over 2 sigma squared. There should be a minus log z for the normalization constant, but then z doesn't depend on phi. So z is just the z of the prior, so it doesn't depend on phi. So I can ignore it in the optimization. Okay, so now I've got, this is the thing I'm optimizing. I'm still just following through on the Bayesian maximum a posteriori optimization problem. The next thing I can do is divide by n, divide by the sample size. So so optimizing this is the same as optimizing when I divide by the sample size. Pushing that into this sum, this just becomes the cross entropy. It's just an average over the training data, averaged over the training data of minus log probability of y given x. So this is our cross entropy loss. And we get this extra term corresponding to the prior probability distribution. Note that there's a 1 over n here. This is what we're dealing with now. This is what so if we take the gradient of this, right? SGD is going to want to take the gradient of this. This is the thing we're trying to optimize. If we take the gradient of this, we just get the gradient of the loss, pushing this gradient operator in there. This is the gradient of the loss. That's what SGD works with. The gradient of this, the gradient of the norm squared, is just twice the vector. So the two cancels, and this is the gradient of the log prior probability. And then if you look at an SGD update, the SGD update says that the next parameter value is the previous one minus eta times the gradient of the thing you're optimizing. And the thing we're optimizing now is the log loss has a log loss term, and that gives us the normal loss gradient minus a term that comes from the prior probability. So we get this additional adjustment here. Note the 1 over n. And why is this called shrinkage? Well, what's happening here is this term is subtracting some number times the current vector. And so we're taking typically a small number, that's small and that's large. We're taking a small number and we're we're shrinking this term is shrinking the parameter vector by some small amount. And that's why in the deep learning community, L2 regularization is often just called shrinkage. So here's if you go to PyTorch and you look at vanilla SGD, there's a shrinkage parameter, gamma. This is the update equation, right? This is the update equation I just derived. What they've done is they've taken this term here and just given it a name, gamma. But we have to be careful here because lots of things can change. You can change your batch size, you can change your momentum parameter, you can change the amount of training data you have. And we want a parameterization that is robust to these changes. So we would like a robust way to calculate robust parameters here that sort of accommodate variation in these other hyperparameters. And we've already argued that the right learning rate in vanilla SGD, if you want to be robust to changes in the momentum parameter and in the batch size, is given by this formula, where this is some kind of universal temperature parameter. Under this assignment of eta, this is the temperature, or is defining the temperature. And what we just derived from a Bayesian point of view was that this gamma should be the learning rate, as defined by this, over n train times a robust L2 regularization parameter, which is sigma squared. So the idea is we have a robust temperature parameter and a robust regularization parameter that are insensitive or less sensitive to variations in these other parameters, batch size, momentum, size of training data. Okay, that's the end of the first unit on regularization. Thanks.